should be able to come from the right to the left. So to start with, the volume of the left hand side is 0, although it doesn't look the way I've drawn it, but it's 0. And the volume over here is V2. And then I push the piston and I take all the way up to the right, so that the volume over here is 0 and the volume over here is V1. Okay? V2. And the pressure is P1. It's a different pressure. And the temperature? V1. So, why not? As well as just write V1 volume. Huh? No harm. If I'm not going to use the equality, no harm in writing V1. So, what happens in the end is that the pressure P1, V1, T1 is on the left, and on the right it's P2, V2. Oh, on the right it's 0. No volume, no pressure. Okay. So the volume is 0, and now the volume is V1. So, what is the work done over here? Is that what I would like to know? What I have done is that when I push the piston, I did not want the two things to be equal, because then it would have been just too obvious, we wouldn't get anything done. So I maintained a condition of irreversibility. I pushed it hard enough so that the pressure is not equal on both sides. Okay, but not very hard, but hard enough, so that it's also not reversible. So it's an irreversible process that I have done. Now, in that case, if it's an irreversible process, going from P2 to 0, the work done is essentially 0 minus P2 V2. And when I have gone from P0 to P1 V1, the work done over here on the left hand side would be P1 V1 minus 0. Yeah. So the total work done on the entire system in this irreversible manner would be P1 V1 minus P2 V2. The sum of the two works on the left and the right hand side. This entire part was insulated. Sorry, I didn't mention that. So Q is anyway 0 and W is that. Sorry, no. That's why we have different temperatures, and that's why we have different pressures. No, it's not constant. No, it's a different pressure on the left. It's a different pressure on the right. Yes. Otherwise, I can't use the equation that I'm using. Okay, so if I've got that, I could just say what my total work done is. My total work done is yes.
So much how do you maintain a constant pressure on side?
The trick was to push it slowly, but not very slowly, so that it becomes equal pressures. Okay. So this is it was a very clever experiment indeed. Yeah, you can imagine. So now what you do is that if you get this, and then the other term that you had over there was delta PV, and then Q was anyway 0 since it's adiabatic. So what I get is delta H equals 0. Now if you can do this experiment and see what is this. So temperature can't be constant here.
How did the volume still remain V2 even after?
No. I said okay, the volume can be anything. Since I'm not going to use that fact, let me just write V1 and V2 separately. No, the volume doesn't remain V2. The volume goes to 0. It's pushed over here. This is my initial condition. Final condition is 0. Huh? Or wherever I wish to bring it to, for that matter. But then I'll have to worry about it. If I bring it wherever, then I have to worry about the V2 final and V2 initial states. Then also it will be delta PV only. Okay, so this is what I get this equal to 0. If I get that equal to 0, then how do I write that? Del H by del P at constant temperature would be equal to minus Cp times del P by del, correct me if I'm doing any mistake, at constant humidity. That's what I would get, I guess. Huh? No, whenever I do these mental calculations, I get into trouble. Right. Okay. So, what does this say? This fellow, dT by dt at constant enthalpy, is also known as the Joule-Thomson coefficient. And different books have different notations. And I think Atkins, what it says is it's eta, which is the Joule-Thomson coefficient. And this fellow, Atkins calls as eta T maybe, because this is isothermal Joule